Hoje temos a honra de trazer Caio Licciardi. Caio chega aqui muito distante do programa de 2 escalas do Canadá e do Atibaia. Originariamente ele é do Atibaia, seu estudante da USP, depois foi para a École Polytechnique de Paris, né? De Paris. E depois fiz o doutorado em Regina, no Canadá, respeito para ele, para quem conhece Gabriel, ele está lá em Canadá, ele está lá agora. Depois ele foi research scientist do Sonava ainda, foi adjunct professor da Canadá University e assistant professor de física no Windsor University do Canadá. Ele vai falar do Majorana Neutrinos com Liquid Xenon.
Obrigado. Eu vou falar por inglês, que é um pouco mais acostumado com esses slides. Mais alto.
Só um minuto. Desculpa. Já iniciou a gravação? Ok. O seminário está sendo gravado. Se você está aqui, vocês dão o seu consentimento a ser gravado. Se você pergunta uma coisa, a pergunta vai ser gravada. Vocês são conscientes disso, do seu consentimento. Depois você vai assinar um termo. Você é o quê? O seminário é sempre gravado. Perfeito. Esqueci da pergunta. Ok.
Legal, Então, eu agradeço a oportunidade de estar aqui para falar sobre esse tema de pesquisa que é o meu principal, que é a procura de neutrinos de Majorana Neutrinos. Off outline, very briefly, we start describing very briefly the standard model. I hope everybody is somewhat familiar with the standard model. So that we can introduce what are new physics and how we can go beyond the standard model. To say then how we go beyond those. Then what solar is and how that lab fits in the picture of new physics. And then the last slides is on this research essentially search for the violation of conservation in the standard model called lepton number conservation. Through a hypothetical routine we call it appropriate routine. So, the standard model of particle physics is a successful theory written in this field framework, right, that describes very well, quantitatively, the interaction between particles. So, the particles in the standard model essentially are divided into
What do you say that this middle one? Yeah, that's one.
So particles in the standard model, they are divided into 2 types. Right? So there are particles of matter, they call kernels, and particles of interactions, and we call neutrinos. So then in kernels, the particles of matter, they are divided into leptons and quarks, depends on the interaction with the so these kernels leptons are in green here, quarks in purple. They come in 3 families of generations of 3. Each family, they essentially have efficiency families, they're essentially just in mass scale, which they have the same numbers. The quantitative description of this interaction is essentially by the Lagrangian, which summarizes these 4 lines, of which we're interested in the parameters. So these 2 lines in the middle. So what they are telling us here is essentially that the interactions between kernels is given by this line, which has essentially, so each particle here is described by the letter psi, and then the particle configuration is essentially like this sidebar. So each interaction between find these two, so that's the equation, is line. So one of the things this is telling us is if you were to assign a lepton number of +1 for leptons for each sides, and that would be a -1 for the side numbers. So for every single interaction, this number, the sum of this number will always be 0. So this translates into practically observations that the lepton number. So we have the same number of leptons minus of the leptons in the initial states, and that we have the final state. This is another possibility. The other thing that the Seminar model is telling us about primitives is in the third line. So the third line defines 5, which is the least. So that's essentially the masters. So what it's telling us is that we have this company Yij, because the masters is mixing the primitives of the how that affects the neutrino measurements next to these lines. So historically, the Standard Model was very inspired by neutrinos. The fact that we don't know everything about them yet gives us additional motivations for continuing studying this particle. So that's basically the Standard Model. With that, we still have questions, right? We still don't know. That doesn't give us an answer on why we see this asymmetry between matter and antimatter. So to try to answer these questions, then you have to go beyond the Standard Model. You have to find physics that is not really here. You need to find software to search for these things. So the first evidence of physics beyond the Standard Model also came from go back to illustrations for physics beyond the Standard Model. Which essentially this is a phenomenon where after several measurements we learned that despite neutrino being massless and inspired in the Standard Model, neutrinos actually have masses. And all zero. That was worth the Nobel Prize in 2015 for one of the spokesperson of the Sloan experiment, Sloan Singularity of Zimmer, and a pressure top from supergame. So what the illustration tells us is essentially because neutrinos are quantum particles. If you have these ideal particle, you can weight neutrino masses. So if you were to make neutrino, we would plot the wave functions with various states of masses that we call neutrino 1, 2, 3. Remember them? Which are different from the states where they interact with the states. The mixing between them is known as PMNS mixing. Which is essentially the Yij computations that are in the implementation. So if you create, so that is if you create a neutrino from a certain type at a certain point, and then you go to back, you can solve these in the mass hybrids, where essentially eigenstates of this evolution. And and these equations are not postulated as so it's a simple solution as usual, where you have these spaces that are equal by the energy of the neutrino. And since you can factor out the global phase, and speed for all of the neutrinos, essentially this quantum effects of this solution is only the difference in phases here. So then, the difference of these phases. Then, in neutrino stations in vacuum model, and measure these differences in the mass squares.
Sorry, can you explain this? So this is like you approximate the evolution of time like Schrödinger equation. Right?
Yeah, this is the solution.
And then
right?
No, because you said approximate, and I don't know how extension of this approximation like.
Oh yeah.
Is this bad or this is like?
Yeah, there are certain approximations that good approximations like neutrinos are relativistic particles. So notified. There are a couple of things you have to approximate because they are traveling relativistically, so shouldn't be the equation shouldn't be the equation used for this, right? But they are.
We know how bad it is.
Quantum field theory oscillating wheels does not exist. Yes.
No,
It's mass of the energy of the Euclidean square. The approximation is mass of the energy of the Euclidean square.
okay, so it's very good, right? Yeah, thanks. Yeah, so that's very good. I mean, to the point where our measurements, even tiny effects of these, we cannot measure, so we can mass deviations from right, so the only thing that important here for our observation is the difference between these energies, like the mass squares. And more than that, I mean, if you look at quantum probabilities, is the amplitude square of the probability within the amplitude square, so we don't even get to see the sign of the difference when we only look at the illustrations. But then if neutrino travel through matter, then you can have enhancements and break these and give us information about the sign. That's how we know the difference between the second mass and the first mass positive, right? Or neutrino traveling through the sun. And we know that the second mass is heavier than the first mass. But we don't know anything about the third mass, which comes from another source of neutrinos. So the third mass, we don't know if it's heavier or lighter than the first mass. But we do know we have different amount of matter. So if you place them in this diagram, where you have masses started by lights to heavies, and the composition of 1, 2, 3 terms of the bunches of electron and tau neutrino, this is what we get. For N1 is composes the most electron neutrino, or vice versa. The largest contribution for N1. So you expect that N1 is the lightest, but because we don't decide, we don't know. So to this day, we still don't know. So we always work on these two possible configurations where we call the normal ordering, where it says N1 to be the lightest, because it kind of goes with the intuition that the electron is lighter than U1 and tau. But there's also the possibility that it may be inverted ordering realization, but we don't know. Right? It's becoming less and less probable with the stationary systems. Right, sorry. So the other thing I forgot to mention is, I like to take the experiment of this just to see, I mean, often you see this efficiency experiment, but that doesn't come much where we give this efficiency masses, and if you take the experiment, you see that one difference is about 10 electron and if you the difference for the one is 15 electron volts. So that's low energies, right? So that calls for low energy experiments for the most part. That's why we use low energy experiments to find new physics. Low energy experiments are these experiments where we're looking at events that are of the order of EV, or some EVs, events. And this is where natural radiation lives. So if you're looking for new physics there, you must be looking for something that's very rare, because otherwise it would have been observed, right? It has to be very rare. So we call this physics of rare events. And the main candidates to find physics in this region are today dark matter, which is this hypothetical particle that maybe might be a kernel that has a very unique interaction rates. But it would be a new type of particle that explains some of the observed phenomena or gravity. Right? And the other candidates is the search for Majorana particles. Majorana comes from the name is from a scientist that first hypothesized a particle that would be its particle, so no electric charge, and then we go like to split between particle and particle, because it can work. It has to have mass. And the only particle in the standard model that could be a candidate for this type of particle, so we look for testing whether the neutrinos are there or not. If this is the case, if neutrinos are the antiparticles, then this term here, even when you have a -1, it goes over the cancels that number. So if you then have captures where things are converted to non-neutrino, two particles in this term, violating this lepton number. So this is the most straightforward, say, way to search for Majorana particles, searching for processes that violate the lepton number. So to this date, we believe that the most sensitive search for this violation is through the search of this hypothetical process of the but beta decay is essentially very well known process that brings neutrinos from a nice stable to a more stable ratio of neutrons and neutrons, bringing the nuclear energy to lower states. So that's the beta decay. Double beta decay is can happen when two beta decays occur essentially or simultaneously, but it has to be always the nucleus to a lower energy state. Certain nuclei are very interesting because they have a configuration, some of them exactly like this. So we're looking here is just the energy difference between variable nucleus and other nuclei So in case of xenon-136, in the beta decays, and the nuclear energy would go up to 136. So that's forbidden. But if two beta decays of this diagram shows what will happen, then xenon-136 goes to barrier 136, which is completely allowed by the standard model, not zero. And that's how the probability. So we look for double probability in this type of nuclei because having a single probability division, you can only see double probability. If double probability is permitted and single probability is permitted, then it's just more difficult to see because you see only like single probability all the time. It's a lot more figures because you don't always see. So simultaneously can happen. So the hypothetical decay is like the double beta decay, where you don't have any neutrinos in the final state because assuming that neutrinos are they're all antiparticles, there is essentially a free here in charge in particle type that makes the neutrino participate of both system. So because
they cancel each other, it's like they collapse.
They don't cancel, it's the same particle. It's just that it participates.
The same particle is like divided and participating in both cases.
Yeah, it participates in both cases. Yeah. So this is just intuition of what would be desired, right? But I mean, anything could happen here. Because you won't be able to look into the duplo state. What you'll be able to see is the initial state and the final state. And there's a theorem that tells us if the final state is equal to electrons and no neutrinos, then the neutrinos are Majorana particles. This is the black box theorem. So we search for this, and that's all we can do. An observation on the probability is it would show physics beyond the standard model because the violating the lepton number, that was the final state of the lepton. So the theorem proves that these are then Majorana neutrinos. So the rate at which this process happens then has to be connected with the mass of the neutrino. That's the V, that is the term and U bar. So that will constrain the neutrino. Yes.
The height gerando the electrons fall the same energy, the fixed energy.
No, it's a distribution of energy and reaction. So they don't go always back to back, and they don't go the same energy. So there is a distribution there. It's not as simple, but it would be very nice if it goes back to back, because then you can do detectors that look for these reaction. Because I'll get later in research on like this ratio distribution. And then obviously it help explain the asymmetry between matter and antimatter because Majorana Neutrinos, the possibility of other tools if you alright, so convincing that the probability is research, how do you build a probability in that? So you have to choose a liquid that has this forbidden single probability and it's allowed the probability. There are 35 isotopes. There are some criteria of selection. Many candidates today are 126 and 176. These are the ones that's there are big competitors like the Resumo 130 and recently not very good, but we do research as groups. Then you have to do an activity factor. And so the nice thing about and 76 is the G value of this decay, like the energies which feel like it's an energy is 2 minus 1. 2400 kV and that is 2000 kV. That's why we go for a peak of the natural. And that's kind of high in the natural radiation energy state. A lot of natural radiation that we give backgrounds that look like the signal come from the chain of the target 232 and the chain of the negative 238. It has various peaks. The largest one, the target 232, comes from having to wait 2.6 centimeters, so that's just a beautiful peak, but it's sufficiently beautiful. But for the negative 238, in the chain, there's a decay from bismuth 214 that makes the gamma line of 2.4 that you cannot distinguish so well. So you really have to do a careful construction of the detector to have these detector as soon as possible from the memory. They will also have safety. So Xenon can act as active detector in the sense that it decays, but as it decays, it also responds to the decay, and then it detects the response. So it works as a source of the decay as well as the detector. So you can give a homogeneous detector just with Xenon, then the problems. Even that's a little layer and a little layer, and then you have to come up with detectors from all the domain interactions. So then we do a selection criteria saying energy is not an RP value, and reject the quality is so on. So then you can actually get number of quantitative events, and then you can do number of quantitative events in the features, and then you can find the lifetime, the number of observed nuclei to get time of a half-life of the that really works. Now, great experiments are of the order of 100 to 500 kilograms of xenon, of the order of 100 kilograms of uranium, and they are placing limits on the fuel solubility in a half-life of greater than 10 to 25 and 6 years. It's really long times. What that translates in the experiment in terms of counts is you're seeing essentially 1 count every 15 days. So the detector is clean enough that it doesn't activate every 15 days. But going further, the next simulation of detectors with probability, we expect to set limits greater than 10 to 28 years. So that means we have a detector that's much bigger, rather than cones. But also have to make in a way that's even cleaner with less than a count per year. So it's not that we won't have any counts because people some application numbers in password, we count 10 decays every second. So there's a lot to have the detector that's completely clean of all these other decays. Even Xenon, the probability decay is rare, but 100 kilograms of Xenon, you'll see one probability decay every 10 minutes. So what does that mean is that it's counted in your region of interest. Like after you do your energy selection, your quality selection, you only see 1 count that could be, or less than 1 count that could be seen. The other thing that also is on the way of doing these search for rare events of the neural flux. So we do the fact that that's a part of the expert in the synthesizer. We would next go on the surface, like at sea level, about a neuron every few seconds. So that if you were to view this neuron every second, you then cannot see anything on the detector because of the time you can walk the detector. So that's why you go underground. So here it's showing the neural flux reduction as a function of the depth of the underground blocks. So we have the shallow blocks, we have like the reduction of magnitude, and as you go more and more underground, you get even a reduction of 600. So really get rid of all the neural magnitudes. So that's why it's no lab, and that's why you use no lab. But if you're searching for rare events, you don't want to learn that neurons on your way. Right, so I guess, yeah, so that's NOLA. So NOLA in Canada is a secondary title. It is hosted by a mine, by Vale, that is South Region, essentially a company. Today it's a large 2,000 room area. It's led by Queen's University, but has other universities that are on the field. And it's funded by the CFI. The main experiments is not has today, I don't know, 10, 15 experiments. They're mainly looking for dark matter and things that will benefit. But they also host other projects that do biological or technical science, like biological in the sense, like, so there's a neat experiment that brings flies from surface underground every day to see the survival rates of flies, survival rates of male flies versus female flies. So that's just showing how work underground affects the miners, for example, right? So we do some of these things. So yeah, so here I thought now maybe show this video of Slova. So that it's a reason because that's a video. We kind of covers all snow labs and so that was the surface snow lab, and then here you're going underground, and then I talk about longer underground underground, using obviously mining years for you to get the lab. That's what the second year lab. You get a lot of dirt, and then you actually don't take a shower, so then all your mind years off, take a shower. Yeah, it's just like, no, it's, underground is very contaminated with data. That's what I'm doing. So, you see, so they provide us with a lot of very computers. That's the cafeteria. Is this a food? We only have to so we have to we should really $8. So you just often have to for example, the soup sheets. It's not huge. 2,000 is 3,000. So this is where it is no experiment. This is no event display, but they use for snow plus as well. Everything is snow plus. It's basically the same from snow plus. Exactly, we have to turn the headwater over the they have something. There's a huge quality system. So here is another large pattern. So I'll call it where you they have nice machine shop. That's it. But also, so this is, I think, yes, I think this is the and here is the the thing is only for the next is less active, but now it's made by other, which is the other carbon called yeah, going up and down things like 30 minutes, sometimes more, depends if you get levels to other levels. It stops every time. It's 2 kilometers underground. So you can see, you don't need to just straight to the car, you take but in that way,
vai para Adobe, lá embaixo. Adobe, quando ela chega. É isso aí.
Right, so the one copy that didn't show in the video was built to host a large cryogenic experiment looking for leptons. Just like nEXO, for example, or Majorana Neutrinos. This is a picture of the carbon that's essentially empty. You see some stuff here that these are 3600 because we're using it. 36 is the key houses around here, and we're using stuff here. Essentially empty carbon that was designed to be flooded, right? So you're thinking about a cryogenic experiment. You're thinking of using some sort of a cooling liquid. So if there's an accident and the liquid leaks and will flood, so the way carbon is built is so that it floods but doesn't affect the rest of the block. It's designed to be flooded, but it's not designed to be flooded, right? It's designed to be flood safe. So it doesn't affect the rest of the block. So that's not where we, that's where where we intend nEXO to go. nEXO is the project that we do it's essentially just a big, it's a big water tank that helps deal with heat loss, of course, but also radiation from the top. And then in the middle, we have a few spheres, so a vacuum. Here one has and then our detector is only like about 1.5 So I explained this better in the next slide. So nEXO is really the idea of nEXO. 100 people was successful. With 100 kilograms of liquid xenon. It's a TPC in the sense that TPC means time projection chamber. So what that means is for every interaction that happens in the xenon, we can demonstrate where the interaction happens 3D. Right? And the way this is done is by, so if there's some ionization with the xenon, we have an electric field, so I will happen. We have an electric field that gives this ionization across wire planes, so you get 2 directions of radiation. And then the third position comes from the difference between interaction time and the arrival time of these things, because during the interaction, there's emission of UV light, and then it's affected by this process that it goes behind the others. So if there's interaction, there's UV light emitted, the UV light goes speed of light. The TPC, this is 40 centimeters long. It's like about a fruit. Right? A fruit is like 30 centimeters. Then light travels a fruit per nanosecond. So light travels a detector is like 1 to 2 nanoseconds. Our electronics only reads at the microsecond. So for us, this travel time is instantaneous. We can't see any The electrons, however, that they breathe, they give several microseconds. So it's really a long travel, and then it's not instantaneous. So you can take the time of the light, you divide by the time of the light, you do the difference and multiply by the speed, you do the speed by the electron, and you get this electron. So that's what the liquid xenon TPC means like having a liquid xenon detector. Liquid xenon has to be around -100°C, where you have to do position reconstruction. How good is your resolution? That depends on your wire pitch and your time. So we had two phases of data treatment. That was a successful experiment that ended in 2018. And was the first one to observe an innovative case of 2 neutrinos from 0.6 and total after 7 years running, but a lifetime about 4 years, 60,000. So it's really rare, but if you go for 10 years, you get thousands.
You observe the multiple case, but you don't know if there are no neutrinos.
Yeah, no, these are two neutrinos. Yeah, so then when you look at the spectrum is just like
You see the missing energy.
Yeah, but when you look at the spectrum is just like an ability spectrum, but you don't see anything in between. So these are the two phases. Here's energy versus out. So in the first phase, you see the nexus. So this is a feed for the output shape for the neutrons of the group. So it's a nexus. So when you look at data in this region, you see like 39 grains in respect to the 5 each. It's not really nice. It's not so very likely. So some of this is but when you look at the second phase, there was a depth. When you add them together, you get about the same. So it's really like excess here and there's no excess under so essentially, so I was just going to explain very quickly how the analysis is done. Yeah, for instance, something zero is the energy resolution we can measure from UV light, it's a situation as well as how can we give the light. So we get this stream resonance correlation, getting more UV light, less charge. So we see these islands, energies, and get so if you just essentially project these guys on these axes, right? We have large radius, right? If you rotate your energy axis, right? And you get rid of the correlation, and you get energy level of 1%. The nice thing about it is that the alpha, beta, and gamma is because energy difference because alpha is much heavier. So in these plots, you plot alpha, they come around here. And you know it's very easy to separate if there's an alpha decay versus a beta gamma. Beta gamma have very similar dispersion. There's also the topology discrimination. So backgrounds come from gamma interactions, like we're looking for double beta decays. Variables. So if a gamma comes in the detector, the quantum scatters with the liquid xenon, and that gives multiple deposits. So oftentimes when we're looking at gamma, we're looking at multi-side things versus beta that we're getting single side. A beta that you buy at 2.5 degrees, it will only travel 3 millimeters far. So it's really small. The pitch in the difference of the wire space we have 209 millimeters. So we don't do as good as 3 millimeters, but you can then separate things like multiple deposits from the 9 millimeters versus. The nice thing about liquid xenon is most of our backgrounds comes from the outside, and there is a self-shielding from liquid xenon. So most of the gammas will interact with the edge, making the inner part very clean just with xenon decays. ISO 200 is not very large, it's only 40 centimeters, and the estimation should be making about 10 centimeters. So being 40 centimeters, the only radius is more like 20 centimeters. So two attenuation ranges is not very improbable. But if you go bigger, 10 attenuation ranges, then it's almost 0. So that's the idea. That's the idea of nEXO. nEXO is like a big ISO 200 with some minor technological improvements. I think the main feature of nEXO is that it's not for centimeters, it's one, it's a year and a half, so 70 centimeters. So you will attenuate all that from lots. So you really have to worry about the energy resolution that's a little better than 1% because I don't have control to detect things. You put this on the surrounding of the detector, meaning more coverage area. Just that it's equal to install the sites that I was not ready. Also making the pitch, so it's not wires because it's bigger, it's not big, it's not wires. It's not impossible, but one idea is just to strips charge pads connecting in a row. So we just have a layer of this plate rather than having the wires. So we charge it down to the top and then back to the But now that's basically nEXO, right? So we try to have output kinds of apps, so it's one vacuum, data kinds of apps, that holds data queue, it's the liquid, and then you have our tipsy that's in the output, with then so late 2021, late 2022, we published a very detailed calculation of what we expect from system. So this is the main highlight of the paper. It's a very long paper because we go extensively on like describing all types of backgrounds and trade account for and so on. But very briefly, we separate our background types in three things. So one is just random, gassing, so this is random components that we then have increase the reactivity of materials that we give to the reactor, like copper, so when we assume here our copper is like so it's a technology made by the Pacific National Laboratory that essentially is pure copper. So we have like zero uranium and zero copper, which is almost impossible to do otherwise. So we don't have any contributions from contributions we have in nEXO to nEXO. So really the largest component we have is this uranium. That in nEXO, you don't really know where that came from, it's your understanding. But we assume that in nEXO 200, we have to measure that. We have 200 atoms are labeled with Liquid Xenon, 16 compounds. So in nEXO, we're assuming a maximum of 600. It's really difficult to build something. Just to give you an idea, particular experiments with a Resumo, and they look the amounts of rainbow they have is of the order of 2,000 to 5,000 atoms in statistics. So that's what they did, but for them it's not a problem because they're not looking the same stuff. But just to give you an idea of the challenges that nEXO has is to build a detector that has less than 600 atoms. That's why it's not a problem. That's our target phrase. It's less conservative, it's conservative. So the sensitivity of nEXO to locality would be at the functional gates. So this is a solution for there are two curves, one is sensitivity to exclusion, we don't see anything. And if you see something, what is the half-life? It is something that we can see in my confidence level. That's how it works. But is there a pop-up variable? And here is the physics of it. So if you did in this work like normal battery, these are classes, the regions allowed for these mass that dictate that drives is on the y-axis. So as a function of the minimum and when the normal ordering is somewhere around here, and so you have it has extended out to here, you can somewhere. nEXO extended so still this is the degenerate things, the masses are much larger than the mass differences. Whereas for inverted ordering, and that's why we're doing this design, nEXO would be the entire regional operation. So the idea here is nEXO could make a statement on by another nature of neutrinos if behavior in right? So if neutrinos nations measure the argument that tells us the behavior argument, and nEXO doesn't see anything, and it's not known. And if you say something, it's like that,
Sorry, I didn't understand. So you're saying that in the case of the vertical order,
Yes.
you don't find all that.
Yeah, if you go here,
it's not like this.
Well, yeah, exactly. If the demonstration experiments tell us, yes, it's inverted, and you don't see anything out of it. Actually, it's the same thing like this. And then you're not knowing. But I mean, the real oscillations are there. 90%, 95% say it's normal. 90% will be normal. Then we need to go and develop the experiments and run.
So, giving the neutrino oscillation state is a confidence level.
Yeah, it goes to like 99.7 and no problem. But I mean, I don't think you are no problem saying that. I do. So yeah, so now we look very briefly at the scientists. That's where we are now getting up to is because of the regular problem. It's a control plan in nEXO, doing such a problem. It's a challenge. We're getting up to do the lab that we have, the experiments, assay all the components, the algorithms, so that we can achieve this kind. So we don't have anything, but we are really getting first step is to do something like that. It's something that somebody has already done. So the lab has this nice, it's not complex, like actually, I think, since we have 5 million problems, so we have the essence, so we expect some possible a collaborator of nEXO, so we do something like this. This is a exercise, that's something we have to do. Another thing, is going beyond nEXO, right? So if we live in the normal order, we need to achieve 1 million atoms. So I'll go very fast now. So there are 2 challenges to go beyond that nEXO physics, beyond inverted. One is really a larger detector, and the other is making a better analysis. To build a larger detector, I think that's where the main problem is. Right? Today, we produce about 50 tons of natural xenon per year. That's the worldwide production for the English. So this Western less. So I mean, if you want to go beyond nEXO, you need at least 1,000 tons of xenon. And produce 50 tons a year, we're not going to So we're now the community designing together from different experiments to see, start talk about how we can get to the ton state eventually. Because the analysis type workshop in October, where it's very, let's say, it's a very early stage of talks on how to get more xenon produced. On top of that, this is natural xenon. So natural xenon has about 90%. So the other thing that what we look into is how do we reach more xenon and practice xenon. What we do is we put xenon in a centrifuge, and then you centrifuge, and then you get anything that goes from and right. Still something I do with the parts. To get the edge, xenon, and that's where most of these users are looking up to 90% xenon. But there's a lot of power consumption on this process. So there's something that's cheaper than the light. So our group is investigating using distillation for this. So this, I think, is the largest highest challenge we have to work with. But you can also look at improvements in technology to do better fluidness, right? Making it bigger, something will already happen. Better spatial resolution and better energy. So in blue here is basically by solutions on this stage. So the enrichment of xenon, so we have the xenon steel project, it's so large, it's important. But we have the distillation column and is measured vapor pressure difference of the isotopes. So we have decided, so there was no reliable measurement before inside working with these. Now we have a measure of 20%. Of the vapor pressure difference for 0. Vapor pressure is the difference that drives the distillation, right? Essentially, it's different boiling points, but here this is we talked about because the boiling points are different by 1 or 2 neutrons, it's very close together. For measuring vapor pressure using we had a steam power universe, so that was the prototype. Interesting that we saw with solar, the pilot with 8 modules or something. It's the same setup, and we have 8 modules. There was 2 meters, solar, the pilot was a and the reason why we put the pilot is because we have access to the pilot and top, not because it's underground. It's just like it's very tall and you have access, and it's a lot, so you also have so the result so far, what we can get from this is so that's the pressure of the line of the input. So we have so these are the spectral measures. So measures for argon, and reason because argon we can calibrate on the detector, we validate this assumption we make to either the xenon the spectra, and here is how we do our results compared to other existing data. So our results in that existing data is like these white points. We have some pink points, marble, and then marbles are the models. Right? So marble is the calibrate, so it's very on the top of the model. Crypto is a validation, and xenon, our measurement agrees with the model, because only one previous measurement that didn't agree, like 3 times smaller. So people didn't believe this. It doesn't make the two models, and our work essentially shows it's not right. Maybe there's a big error particle, but because it's all measurements of the pressure, we didn't have any error particles. Anyhow, so these are results from Canada, from Zola. Only so far, only had iron and components. But the point is, at Scarleton, calibration had this 525 centimeters, sensitivity of this parameter. That is the calibration parameter. And now it's Zola, our mass estimates get very nice, so we reduce the sensitivity of that's how calibration goes. Zola. So I wish you can say over and analyze the different we make the decision. But at least we get better solar errors. The other thing we're looking at is better topology discrimination. So we want perhaps to be able to do something that the next group does with gas, which is to measure the electron that comes out of the double decay. And we are able to say there's one electron or 2 electrons. If they come out opposite sides, that's easier to separate. If they are pretty cracks, it's just not difficult. So we have a prototype of how we want to look at this. I won't go much easier. But I think the important thing so far is that we have to looking at if you work is near, well, simulating one level event or 2 level events at the same energy. But if you work is near these events, we need the resolution as at least about 25 micrometers to be able to tell 1 versus 2. So we need a detector that does 25 micrometers. So we're not there yet. nEXO, we have pitches of 6 millimeters, so it's very so we have some ideas that we perhaps in the it's not so easy because there's already if you don't have the yes, so these are the things that are very good. But I want to point out just that we're trying to look at Windsor, so this is a lot of people reminding. So we're just saying we're trying to do it, and not comfortable. We're looking at students in those houses.
Perguntas?
Aí, Marcelo. I have two questions. What is the timeline for nEXO? And what is the situation of your competitors? Since we have a big competition in the field of game, especially with German detectors and Quore Legend. So, what is the competition?
Yeah, I mean, there was this competition for a while until 2021, where UE was saying that they would select only one experiment to go ahead with. But then in 2021, they had this review in summer, where honestly, Legend scored better than nEXO in not points. But that didn't go into the report because the final conclusion of that review was, well, first, pure PhDs, the next generation of pure is cheap, so they would fund it. But Legend and nEXO, they are very important, that they both should be funded, but UE didn't have the funds for either. So the recommendation was that they were going to start R&D for both of these, so they're both CP1 now. But the collaborations are now in charge of trying to find partners around the world to see if more international funds will be available to build nEXO to facilitate the mechanism. So they are supporting CP1 for both, but they don't have a clear picture in mind how they're going to fund out there.
So nEXO is a CP1 level now.
Yes.
So
they're getting some millions now for R&D.
the 2 years in case of
Yeah, I know the
CP2.
Yes. So, likely 3 to 5 years. Yeah. I mean, I also run the Xenon Institute project that's in the Caio. So I keep asking Mr. Lab how long I still have there, because I have to leave when somebody goes there. They say maybe 2 years. Yeah, so that's the good news is they're both in CP1. The bad news is that they don't have money for either of the experiments, so it's still like an open question mark how they're going to play. I mean, I think my recollection from the reports that both Legend and nEXO, they cost roughly $300 million.
What about Quore? Because the technology is very different, the potential for energy resolution.
Yeah, so QP is the future of power. I don't know what details, but I think they're cheaper. Majority of 50 millions, and they're going to be funded. But they don't get to 10 to 28, right? I think they go maybe down to 10 to 27 after 10 years or so. It's not, there's no idea 10 to 28. But it's better than 10 to 26. That's why I'm thinking 10 to 27.
I have a question. You say that if you find a neutrino that will validate other than the other obvious, it might lead to a direct measurement of the neutrino mass.
Yeah, it's constraints, right?
Is it a better constraint than other?
Than partícula or other?
Yeah.
Well, there's well, next is but there is one rule. I mean, some papers that show these ones. Because there is a relation between these NPD is something with LND, like in some. And I'm sure that tool is probably but I don't know the compound is NPD. They go somewhere around here, but I think Mexico is. But then, I mean, it's a little something. I mean, there is one part, this function, where is.
Yeah, I see the. Okay. Thank you.
As you mentioned briefly the one experiment, and you said you're looking at different things.
Yeah, imagine different things. Like you're searching for particles at the level, it's very, very low energies, and we're like at higher energies.
Okay, so that was my question. So the diffuse neutrino electrons are proper.
Yeah, no, it's not. Yeah, so the problem for us is anything that lies in 2.4 any dimensional. So they don't use, but for them it is.
And there's no magnetic, for example,
Usually, no. Going back to Semi.
Ok. No questions? Not? Muito obrigado.